interviews, we've questioned other people who've taken part Google Code, and some people who might have been winners before. And for me to understand how Google Coding can benefit a person who's looking to make it in the world of technology and coding, we need to understand the perspective of somebody who's taken part in the competition and also somebody who hasn't taken part in the competition. So, Aras, my question to you is that as a coder, how do you think, like, how was your life without taking part in Google Coding, and how would it have been different if you had taken part in this competition? Just your views on this.
So firstly, I think it's a pretty good question, and yeah, this is something which I kind of regret not taking part in now. Looking how you guys have, actively taking part, and I feel that had I probably taken part in this today, I might have been, a better coder at an early age, and I might have gotten more exposure. And like for example, I probably started coding when I was in grade 10th, and when I was grade 11th and 12th, and I probably would have picked up coding faster had I started earlier with Google Code. So I think it's a brilliant platform for youngsters and people like you who are taking part. And yeah, I just wish I could have taken part in it earlier.
Okay, yeah, that was one of my main questions. And also, what are your tips for somebody who's, somebody like me who's just getting into coding? Like, what's any tips you have for somebody like that?
So, firstly, you need to understand what coding is about. It's just not just learning some language and solving basic problems. It's about approaching a problem. How do you approach it logically? You have to break down the problem, right? So, if something you have to code something, you have to see the you have to RCA root cause analysis of the problem to see, okay, this is what it's made up of. So right now, at a very basic level of coding, you don't have to worry about a lot of things. For you right now, probably it's basic syntax, basic statements, but as you move on, you realize there are things like memory management, time complexity, and memory complexity. Those kind of aspects come into play. So as of now, I would suggest, if you're starting out as a coder, a language like Python can be very helpful. It can give you a very good insight in the coding world. And as you move up the ladder, probably a language like C will be very important, because C is, people say it's outdated, but it's the basics, is the crux of coding. So you should probably start with C, and C will give you good insight how memory is played with, because that is the basics of a language. Once you're done with C, then you can obviously move on to a lot of languages nowadays. There are a lot of fields available. You have data science available, so languages like R are there. And for somebody who's interested in web tech, web development, you have JavaScript, Java there. So there are a lot of domains involved. So it's not just restricted to basic coding nowadays. It's just developed. But yeah, these are some of the languages you can pick up. And I think platforms like code.org, you have Geeks for Geeks, for example. Those kind of platforms are very good for practicing problems. Hacker Earth is there, Hacker Rank is there, and Code Chef. Those kind of things are very good for solving problems. So yeah, just keep practicing, keep exploring, just keep surfing the web. There's a lot to learn.
Okay, yeah. Thanks so much, Aras, and thank you for coming out. I mean, I'm pretty sure you're busy right now, so you'll have to leave. So thanks a lot.
No problem. Thank you so much. Thank you so much.
All right, right. Thank you so much for taking time out of your busy schedule, and I know you have a lot of work, so thank you so much. So let's
No
proceed.
problem. No problem.
All right. Okay, so now let's proceed to the next order. So, Yumos, you want to start?
Oh, sure. Yeah. Okay, so I'll be presenting like a how-to on how to use Mercurial to create a bundle, and then yeah. So should I screen share this? Hold on. I should probably screen share this application window. Sure, my you know. Hold on a second. Okay. Hmm. Can you all see my screen or
Oh, I don't think I can see it any longer.
no? Not yet.
I can't see it either.
Oh, no.
All right, I can now. I
Yeah,
can.
yeah,
We
yeah.
can, we can, we can.
We can? Okay, alright. Alright, so yeah, basically, like I said, I'm gonna be presenting a how-to on how to use Mercurial to create a bundle. So to create a bundle, it's like basically it's like a copy of Python, like to create a bundle of Python. I mean, so basically in many tasks, where you need to change the library, like you need to change the Python itself. You have to upload a bundle as the result of your work. So to do this, you just need so you need to download a fresh copy of Python, which I have here. I've already downloaded the Python, right? So we can just go into the Python, and then we can see this is the main directory of Python, right? And then so let's say my task was to like change the color of um a cube in an example code. Hold on, let's see. Let's say I want to modify cube and sphere stop Python. So let's say I want to change the color of this cube from red to blue, right? So I would make my change here. I will change it to blue. I will save it. Oops. I would I'll save it like this. Then I would run it and to see if it's changed or not. So as you see, the cube is blue now. So my change has been made. And now I go back to the main page of the Python, and I use hgdiff to check the changes I've made. So here you can see that the only change I've made is in cube and sphere.python.py, and then the change I've made is that I did the line where it makes the cube red, and I added the line where it makes the cube blue, right? And after I checked, and then like this step is important because so you don't want to change anything other than the code that you are supposed to change, right? So if you change something else, then it could cause a problem for other people if they actually use your code. So so if you check this hgdiff and you have made sure that you only change what you are supposed to change, you can commit. You can use hg commits to commit your changes. And here you will leave a commit message saying that what you've changed. So I will say I changed examples cube and sphere.py, and I will say changed cube from red to blue, and I would control O to save, and I control X to exit this. And then now it's committed, I would use hg bundle, and then I will use R, which is in the version. And for me, I use Q668, which is like one version later than the current version of Python that you have. Like if you check on the Python website, you can see that the current change set is 2667, and then yeah, if you just put in 2668, it will work. And you put in A, and you just make a name for it. Let's say you want to call it bundle January 4th, right? And you just press this, and then it will bundle up it will change it for you. And then you'll be able to see your bundle here. And then we can test if this bundle works or not by unbundling it in another folder. So I'll just go to where was the Python? I'll just take this bundle to my home, I'll create a new folder called very fine PySoy, and I'll put a bundle that I've created into verifying PySoy. And then I'm gonna cd into verifying PySoy, and then I'm gonna unbundle it. Unbundle bundle for Alright, and now I've unbundled the bundle I've created. And then I can check if this bundle works or not by checking the code I've changed. So I'll just see the examples, and I'll check for this one. So you see here, the code is blue. So that means this is the code I've changed and it worked. Yeah, that's all for meeting. For presentation.
That was really informative. Thank you so much. So, Alpha Thesis, do you want to go?
Sure, I'll go ahead. I'll share my screen.
Wait, before that, does anyone have any questions for Yumozi?
Not really.
Yeah?
No,
I
but
think he
thanks a lot. It was
provided
really
very-
informative.
Yeah, it was very holistic in its approach. Anyway, should I start sharing my screen?
Yes.
All right. I'm hoping you guys can see my screen right now.
Yeah, we can see it. Please go ahead.
Yeah.
All right, sure. So I'm going to talk about how the rendering pipeline for OpenGL works. I've drawn up this presentation. So firstly, we need to understand what a rendering pipeline is. So we know that we enter certain blocks of code in order to render 3D images to a 2D screen. So what a rendering pipeline is, as it mentions, a conceptual model that describes what steps a graphic system needs to perform to render a 3D scene to a 2D screen. So I'm entering a certain block of code, then a certain sequence of steps is performed by the system, by OpenGL, before it gives us the end object. So I'll run you through the process. So it's a 9-step system. However, as we see, so earlier we used to use legacy OpenGL. Now we use modern OpenGL. So in legacy OpenGL, all of this had to be done manually. Right now, it's mandatory with certain optional and certain programmable steps. So as you can see, I'll just draw up the perfect system for OpenGL, how the entire pipeline works. I'll go to Wiki. And right, so this is the rendering pipeline. So as you can see, this is the overview. This is brief. I'll take you slightly more into it. This is the system we're looking at. It has 9 steps, some optional, some programmable. Getting back to the presentation. So the first step is vertex specification. In vertex specification, we write a certain block of code. So we list an ordered list of vertices that define boundaries of the primitive. Now, the primitive is what we're trying to obtain on screen. So along with the ordered list of vertices, we often tend to define attributes like color, texture, coordinates, and similar attributes, similar physical attributes that we're trying to obtain in our final rendered model. Secondly comes the vertex shader. This is probably one of the most important parts while we render of the pipeline. So we have a certain specification. Now it's made to pass through a vertex shader. Now the vertex shader is a program that manipulates the vertex data. Now shaders are executed once for every vertex. That is, say we have a triangle. So a shader is executed thrice. If we have an object with a million vertices, then the shader is executed a million times. And the ultimate goal is to calculate final vertex position of each vertex. Then comes tessellation. So there's this is obviously optional, and There's this shader called a tessellation control shader. It determines how much tessellation to do, and it thereby ensures continuity across patches. So if you have two distinct adjacent patches, it ensures that the shared edge uses the same level of tessellation. After this comes the geometry shader. Now the geometry shader, as the name suggests, works on the geometry and then multiplies. So I enter a certain primitive. For instance, I enter a triangle as a primitive. The geometry shader will visualize a series of triangles. So say I want X number of triangles in a repeated pattern on screen. Then then I enter my primitive, say that I need a certain X number, and the geometry shader ensures that I will have X triangles at the end. After that, we have vertex pre-processing. So this is a fixed function stage. I mean, users can't do much. It's something that is computerized. And the most important is clipping. Now, what clipping does is, okay, so there's only a certain amount, a certain part of the picture that I can view on my screen. What clipping does is discard everything that cannot be viewed on my screen, which is outside the viewing value. Then comes almost the penultimate steps. Firstly, we have primitive assembly. So, what primitive assembly does is collect all the vertex data and order it into a sequence of simple primitives. And then we move on to rasterization. Now, rasterization is probably the most important of the entire system in the pipeline. Now, what rasterization does is it takes each individual primitive. So I have 25 triangles. It takes each of those and then breaks it down into discrete elements called fragments. Now, these fragments can be further worked upon based on the sample coverage of the primitive. So we have the fragment shader. This is used very often. This often also tends to take normal value. What it does is calculate the color of each fragment that the user can see on screen. So the fragment shader, deter- all in all, it determines the final color of each fragment. That's all it does. And lastly, this is the last step that we have, per sample operations. Now, per sample operations are certain tests that are performed based on whether or not the user wants to activate them. So there are many tests. There's the pixel ownership test, the scissor test, the stencil test, the depth test, and many more, which I will show you right now. Uh, right. So if we look at this out here, we can see there are per sample operations. So these are the most common per sample operations. Now what the depth test does, which is one of probably the most important. So we have a sample with a specified depth value, and we have a certain object that we're looking at right now, the fragment. And it compares the depth values of both. Once the parameters are compared, if the parameters tend to fail, the fragment is discarded. Otherwise, the fragment is kept. So I'd say that's all. That's primarily how it is. As I said earlier, when we used legacy OpenGL, all of this was dependent on someone doing this manually. However, since we're using modern OpenGL now, modern OpenGL has made possible automation of such things very easily. And I think that's all for today. Thanks. That'll be my contribution to this meeting.
Okay, I think. Does anyone have any questions?
Yeah, I'd be glad to take questions.
I just had like, I don't think this actually counts as a question, but can you please tell me a little more about those tests, those pre-sample tests? Like those tests, like what do they verify?
About
Like you were telling, that you showed like a bunch of tests, right? Like in the
yeah. Oh,
document.
there's all right. I get it.
Like
So
what? Like for example, like what does like you take an example of one and tell what does it verify? Because like the test is supposed to test
all
something,
right.
right?
So I'll explain. So as I took into account, I talked about the depth test. So I'll explain to you about the depth test. Now, what it does is when we specify certain parameters while writing the code, what we do is specify a certain depth of each triangle, and there is an error value. So say I want a depth of 5 centimeter, but a plus minus 1 centimeter is acceptable. All right. Now what I'm doing is breaking it down into fragments. Then I render the entire thing. I break it down into fragments and I have various small triangles. Now the depth test compares my ideal triangle with all the other triangles that I have formed as fragments. Now say some of them have, so I can accept anywhere between 4 to 6 centimeter of depth. However, if there is one that has more than that, say one has 10 centimeter depth, it is discarded automatically. All right. So if it fits within the parameters, it is kept. If it isn't, it gets discarded automatically.
Oh, okay. So that clears a lot of things up. So I
All
think
right.
we reached the end of our weekly hangout. So thank you so much for thank you all of you. Thank you so much for taking time out of your schedule and coming up to the call. I think it was a really informative call, and we learned a lot about the various perspectives on why we should code and how GCI is helping us. And then we went to Mimosi and how we learned about the various mercurial functions and alpha thesis for explaining various things about OpenGL. So I think we all learned a lot. So thank you so much, and I'll see you next week.
Yeah. Thanks for hosting this. You were wonderful.
Thank you.
Yeah.
Thanks,
All right.
guys. Bye.
Yeah. Bye bye. Good
Bye.
night.
Have a great day.